Are my slides visible?
Yes, it's visible.
Yeah. So good evening, guys. Yeah, actually we are late for 2 weeks because of some um, personal issue, and after that the PMRF symposium. So I am continuing the class from the live session 6. So we will be covering up 3 weeks within 2 days, today and tomorrow afternoon. Also, one other live session class will be there afternoon 12 o'clock tomorrow. So today we are discussing about the week 6. So whatever we have discussed previously up to week 5, I think all of you had a clear vision about it. Now we are going towards the next um, session where we are going to discuss the phase modulated optical sensors. So as we just give me 1 minute. Yeah. So moving towards this particular topic where we are discussing about the phase modulated optical sensors. As you know that the photodiodes doesn't really care about the phase. It only detects the intensity if you talk about the um, ADC conversion. So here there is this again. Yeah. So if you talk about this particular modulation where there will be a fundamental detection dilemma. So to detect a microradian environment perturbations from acoustic wave in hydrophone to pipeline gas leaks, we must match invisible phase evolution to measure intensity changes. This requires taking light into revealing its own delay. So you can see that how the propagation phase propagation can be in the environment can be used to detect the pipeline gas leak or like acoustic wave in a hydrophone. So the environment where first figure shows pointer, you can see here that the propagation phase phi is equal to 2 pi by lambda into nl, 2 pi nl into nl divided by lambda. While talking about the invisible shift, so the photodiode is a blind for this kind of phase shifting, and the translation box where the visible intensity changes, it depends on the demodulator. So what kind of interferometers can be used to uh, have the phase mismatch condition? So for that, the first one is the free space or Michelson interferometer, where the matrix, it says that the high alignment sensitivity, maximum to minimum fringes shift occurs in just del d is equal to lambda by 2, half of the wavelength. Then vulnerability will be submicron mechanical drift, and the use case is highly controlled laboratory environments. While the another one is all fiber or Mach Zehnder interferometer, where the laser is splitted using the fiber into 50-50 coupler, using the 50-50 coupler. So this is the reference arm and the sensing arm, and again it's coming to the 50-50 coupler, and here is the receiver. So the matrix for this is zero free space alignment required, environmentally rugged and flexible routing. Vulnerabilities: fiber bifringence and thermal sensitivity. And use cases: field deployment, pipeline monitoring, deep sea hydrophones. Okay, so these are the use of this. Moving towards the challenges using with the phase sensing. First is the temporal coherence. The light must remember its own phase over distance to interference. The solution is source line with matching. Then second one is polarization drift, where the interference drops to zero if the vector angles of the reference and signal randomly misalign. Solution is polarization maintaining fiber. Then the third one is environmental noise, which is 1 by f baseband noise completely buries the targeted low frequency acoustic signals. The solution is phase generated carriers. Then the fourth one is fundamental source noise. Spontaneous emission causes quantum phase uncertainty, defining the absolute sensing flow. And the solution for this is high Q cavity lasers. So moving towards the next thing is like temporal coherence scale, where we need to discuss about the terahertz, gigahertz and kilohertz bandwidth. For this temporal coherence scale, an interferometer is an autocorrelator, and by the Wiener-Khinchin theorem, a broader power spectral density strictly limit the allowed time delay. You can see that the terahertz, which is the broadband LED, has the delta lambda of 50 nanometer and coherence length up to 20 micrometer. And the use case of this is optical coherence tomography, OCT. Then the next is gigahertz, where the fabric parrot laser um, can be used, and delta lambda of this 1 nanometer and coherence length is 1 mm, and this is for the short range laboratory sensors. The another one part is the kilohertz one, where the distributed feedback laser and narrowband lasers usually. So here the uh, delta lambda is the frequency is 1 kilohertz, and the coherence length is approximately 10 plus kilometer, like above 10 kilometer. So this is used for the phase OTDR, LIGO, and remote hydrophones. Moving towards the next thing, which is the fringe visibility envelope. The degree of the coherence acts as a decaying envelope. When the path length difference exceeds the coherence length, and the beating term vanishes, making phase demodulation impossible. So you can see here that the plot has been given um, the path length, distance versus intensity, and degree of coherence is mentioned in the mode of G12, and the coherence length also has been given as a LC from 0 to LC and 0 to minus LC. Now the next thing is like harnessing low coherence optical coherence tomography. For that, the low temporal coherence is not always an enemy. Broadband LEDs restrict interference to matching path lengths, enabling high precise tomography, dicing without physical penetration. So the here the thing is like scanning the reference mirror sweeps the tiny 20 micron interference window through the tissue depth. The path length must match precisely for fringes to appear isolating depth. So here you can see that how the a scan depth probe is penetrating through the tissue, and the 20 micrometer interference window is there. Moving towards the next thing, which is the Frenzel-Arago limit, the polarization drift. In standard circular fiber, random ellipticity and stress cause the polarization state to unprotected envelope. So for that, this visibility multiplier is cos theta. So if the reference wave and the sensing wave returned with orthogonal polarization, theta is 90 degree, the dot product is 0, and the reference fringes disappears completely regardless of perfect temporal coherence. So the visible multiplier is approximately cos theta. And let's see if I'm visible or not. Yeah, it's perfect. My mics are on. Yeah. Okay. Moving towards the next thing, that is the PM fiber architecture, where there are two kinds of fiber architecture: standard SMF and PM fiber. The standard SMF has the degenerated HE11 modes. Beta odd is equal to beta even, and the result is energy freely scatters between orthogonal state, causing random bifringes. Status, phase sensing, and which is unreliable. Then PM fiber comes into the picture, where the stress rods break degeneracy. Beta odd is not equal to the beta even, and the result high bifringens strictly locks the launch polarization in place, zero cross coupling, and status is phase sensing stabilized. Then next thing is like 1/f baseband burial. So real world sensors like submarine hydrophones operates in the low frequency baseband. Here massive thermal and hydrostatic fluctuations drone the target phase shift with respect to time in random noise. Okay, so your phase shift is phi st, and random noise is phi nt with respect to time. we can see here that 1 by F environmental noise is equal to temperature and pressure. Because of that, this is buried inside. So the target acoustic signal here it is at 100 hertz. And moving to next thing, which is escaping the noise, phase generated carrier PGC. By modulating the reference arm with a piezoelectric transducer at a high carrier frequency, we mathematically shift the phase measurement entirely out of the noise floor. Before buried baseband, it is like this, and after carrier shifted PGC, the intensity of the signal enhances quite high, and uh, expanding the interference equation yields Bessel functions. The even harmonics 2fc carry cos phi t, while the odd harmonic fc carry sin phi t. So this is how it happens. Like it changes the signal quality using the phase generated carrier. Then moving towards the next thing, which is the demodulation, the differentiate and cross multiply array. To isolate the clean phase shift, the receiver beats the signal against generated carriers, differentiating across multiplying and subtracting odd even components yields the pristine phase. So for the um, uh, for this is the diagram, schematic diagram, where the raw photodiode signals are splitting into two. Their multiplier use the beat with the fc, and this side 2fc, and both differentiator um, uh, used to forward the multiplier signals, and after that the odd components where the multipliers are used again to mix the signal from this direction and this direction to the another multiplier, and this mixed signal again is coming to the subtractor and going to the integrator, where the phi t clean phase output is occur. We are getting the cleanest phi t phase. The fundamental floor source phase noise. So usually the source also carries some phase noise. Even the environmental isolation and PGC modulation, the ultimate detection limit is set by the quantum mechanics. Spontaneous emission defines the sensor's absolute minimum detectable limit. So every laser produces spontaneous emission, photons born with random phase angle. These random vector additions slightly bump the coherent beam, of course, and creating fundamental phase uncertainty. So because of that, it's generating some kind of, because of the spontaneous emission, it generates the noise, and it's mentioned in this plot. The next thing is engineering the source high Q cavity. As we discussed previously, that high Q cavity also reduces what we have discussed here, fundamental source noise. So it can be reduced by the high Q cavity laser, and this can be achieved by the best is DAB laser. To push the detectable limit down to micro radians 10 to the power minus 6, we must dilute spontaneous emission by locking the phase output into a pristine narrowband state. So the phase variance is proportional to the 1 by tau, under root of tau, which is lifetime. By utilizing high finis, high Q laser cavity, we drastically increase the ratio of stimulated to spontaneous emission, solving fundamental source noise. So either it can be used, either it can be generated, high Q cavity can be generated using the Fabry-Perot cavity or distributed feedback lasing cavity. So here is the example of the FP where the highly refractive mirrors are kept facing each other, and their high average photon lifetime is um, um, this is directly inversely proportional to the phase variance. Then since this is the master plan sensor architecture, so how does it work actually? If you are talking about the phase phase modulating sensor, for that what we do, how it actually has the component. So you can see here that high Q signal longitudinal mode laser, source noise solved, so everything is solved, and proper laser, high Q laser is used for that. Here is a 50 coupler where the one is going to the reference, another is for the sensing, and in reference in the reference, the PGT modulator at 10 kilohertz, which is the environmental noise solved, is used, and during the sensing, the hydrophone mandrel 100 hertz acoustic input is used. Then there will be again 50-50 coupler which is going to the photodiode, and photodiode is again taking the signal to the PGC DSP output, and it will also resolve your final signal quality. So this can be used for the long range communication also, long range sensing application also, where 10 plus kilometer of field deployment can be used. So till now we have discussed about the phase modulation sensing applications and how it works and what are the components we need to use for that, and it's like a recap only. So if you want in more detail, you can go and check the lectures. I hope you have already checked the lectures, gone through the lecture. So we need to go now with the question answers one by one. So if you have doubt till now, just let me please ask me, let me know. I'll solve it, and after that we'll move towards the question answer session. So I'll give you 5 minutes and come back. Yeah. So please let me know if you have any doubts till now. Actually, the thing which I have covered is up to week 8. So up to this week, current week, we have already covered. But this one again, I will shorten it into the small pictures, like um, half of the part where the um, starting of the phase sensing it will be, then the application part will come, and then the question answer again. So do you have any doubt? Yeah, so moving towards the next thing, which is question answer session, where I'll give you some questions and you need to guess the answer according to your judgment or your logic. After that, we'll discuss about this one. I'll give the clarification which one is the correct, and uh, we'll discuss like this. So, the first question is, in the context of inline gas spectroscopy using optical time domain refractometry (OTDR), why is the use of hollow core photonic band gap fibers significant? Option A, they increase the refractive index of the cladding to surpass the core. B, they eliminate the need for a laser source by using ambient radiation. C, they prevent any background absorption at non-resonant wavelengths. D, they allow the gas to percolate inside the core to interact with the light. Give me your answer. You can type also in the chat box. What could be your answer for this question? Can you tell, Joshin? Any hint you can give? Option A, you are saying. Okay.
Yeah, I have gone
Okay.
through option.
So option A, they increase the refractive index of the cladding to surpass the core. But why do we need to increase the refractive index of the cladding? Um, because we have hollow core photonic band gap fibers, so why we need to think about the cladding? See here, obviously the option B is not correct. You can see here easily. Let me go to the slide. Yeah, so here you can see pointer pen, this one. They eliminate the need for a laser source by using ambient radiation, which is absolutely not correct. The option C, they prevent any background absorption at non-resonant wavelength. So it is also not correct. Any background absorption at non-resonant wavelength, how it is possible? It can also absorb with a non-resonant wavelength. So the first thing, whatever you are saying, they increase the refractive index of the cladding to surpass the core. It is not possible because the gas has nothing but very low refractive index. Just a second, I'll take my pen and after that we can do. Yeah, so refractive index is almost 1.0001 something. So in with this you can't think like they increase the refractive index of the cladding to surpass the core, because core's refractive index will be approximately 3.3 or more than that also, because it's a glass fiber or silicon whatever, and core's cladding is approximately 1.6. so this is also not correct. So the correct option is option D, where I'll read it what is written. They allow the gas to percolate inside the core to interact with the light. That's the correct answer. You have the hollow core. This is suppose cladding outside, and you have hollow core. Inside hollow core, if gas molecules are going, then it will interact more with the surface of the core, and that's why you are getting you will get the enhanced data with the inline gas spectroscopy. So that's why this hollow core is used. It will let the gas go inside, and after that you will get the enhanced data compared to the normal. Next question is, did you understood what I am saying? Please be logical, so it will be useful for you. Moving towards the next question. What is the primary function of an optical demodulator in a phase modulated sensor system? Option A is to convert phase changes into intensity changes for the photodiode. Option B, to amplify the polarization state of the perturbed wave. Option C, to act as a filter that removes all noise from the reference signal. Then D is to increase the frequency of the incoming light wave. So we need to talk about the optical demodulator, what it does actually. Suggest your answer. I'm waiting for that. Go through carefully and after that you suggest. Don't be hurry. Option A. So why it is option A, to convert phase changes into intensity changes for the photodiode. That's correct. So what it does is, actually we have seen already this one in the first slide, maybe here. We can see that optical demodulator changes visible intensity changes from the phase. Whatever phase we can't detect with the photodiodes, blind, it's a blind for the phase, but the optical modulators, sorry, demodulator changes it into intensity, just a second, intensity, so the photodiode can easily detect. So this is the correct answer. We'll go for the next options. Why it is not correct? To amplify the polarization state of the perturbed wave, this is not possible. Demodulator, what it will do with the polarization state of for the perturbed wave. So C option is to act as a filter that removes all the noise from the reference cell. That is also, it is not its demodulator's duty. Then to increase the frequency of the incoming light wave, that is also not possible. Demodulator can't amplify the light wave and can't improve the frequency or intensity. The next question is, very good, you have done the nice, you have given the nice answer, correct answer. So next question is, in an interferometer, which operating point is known as the quadrature point, and why is it preferred for high sensitivity? Option is del phi is 2 pi because it represents a full cycle of the wave. B is del phi is equal to pi by 2 because it offers the largest changes in intensity for a small phase change. C, del phi is equal to pi because destructive interference minimizes background noise. And the last one is D, del phi is equal to 0 because it provides the maximum possible intensity. Which one is the correct here? Which is the quadrature point for this? Option B. Yeah, we have discussed already this one, pi by 2. What was the equation for that? This is the pi. Phi is proportional to pi actually. Did I discuss that one here? Might be not. Oh, tau photon we have discussed. Yeah. So this is the correct answer. You are right. Option B is the correct answer because it offers the largest changes in the intensity for a small phase change. That's why this is the quadrature point also it calls. Okay. Other things like 2 pi, because full cycle, it doesn't mean that it will be having the quadrature point, and it preferable for high sensitivity. Also for pi it is not possible, 0 it's not possible. Okay, so very good. Next question is, what is the significant disadvantage of using a free space Michelson interferometer for field application compared to an all fiber setup? What are the disadvantages? Option A, free space setups are completely insensitive to refractive index changes. Second is option B is the high requirement for precise mechanical and optical alignment. C is free space interferometers cannot use monochromatic light source. D, fiber based systems are less sensitive to temperature fluctuations. What is your answer for this? Option B you are saying. So you are saying that the high requirement of precise mechanical and optical alignment. So why you're not talking about the option C? Free space interferometer cannot use monochromatic light source. Will it use or not? So option C, obviously it is incorrect. Everything is sensitive to refractive index. Obviously phase, spatially phase. Then option D, fiber-based system are less sensitive to temperature fluctuation. This is not true. Is it true? Less sensitive to fiber fluctuation. Advantage is more sensitive, so it is also not correct. Then free space interferometer cannot use monochromatic light source. This is also not correct because laser is a monochromatic light source, and the correct answer is the high requirement for precise mechanical and optical alignment. That's correct. So yeah, you are correct again. Well done. Moving towards the next question, according to the Wannier-Khinchin theorem, what is the relationship between a light source power spectral density SV S nu and its autocorrelation function G T? So option A is they are related as a Fourier transform pair. Option B, they are inversely proportional to the square of the wavelength. C, one determines spatial coherence while the other determines temporal coherence. And option D, they are unrelated properties that characterize different light source. So you are saying option A. Are you cheating or what? Everything is correct. Think and give answer, okay? I'll ask you why. Why is it the first one? Give me the answer.
Yeah, I just attended the video.
Okay,
So,
okay, nice.
So I got that.
Okay, because I doubtful because all the questions answer you have given except first one.
And actually, one I was thought of going for the option D because go fiber but I got confused with the part.
Yeah, very good actually. You are doing great. Your answers are correct. You should join every week classes, live sessions.
Because of the time constraint, that's it.
That's
I actually want to attend, but time constraints are there.
Okay. So yeah, this is the correct answer. The Fourier transform pair, and these are all not correct. They are inversely proportional to the square of wavelength. One determines spatial coherence while the other determines temporal coherence. That is also not correct. They are unrelated properties that characterize different light source. This is also not correct. So this is the correct answer. Moving towards the next question, why is a low coherence light source such as an LED utilized in optical coherence tomography OCT? A is to ensure the system is immune to polarization induced fading. B, to eliminate the need for a reference minor in an interferometer. C, to allow the interference signal to be localized to a very specific depth. And D, to maximize the path length over which interference can occur. Please let me know your answer. Already have given. Is it D? Okay, we'll go one by one and we'll see. To ensure the system is immune to polarization induced fading, so you can see that the polarization induced fading, it won't come here for the like it is immune to the polarization induced fading, it won't come here in this concept. Then second option is to eliminate the need for a reference mirror in the interferometer. Obviously we need this, we can't eliminate. If you are eliminating, then you need to use the instead of Michelson, you need to go for the another one, free space, no, fiber based interferometer. Then option C is to allow the interference signal to be localized to a very specific depth. Little bit doubtful. Let's see about the next one. To maximize the path length over which interference can occur. You are saying the is it D? So path length over which interference can occur. We don't need to maximize the path length. This is not correct actually. For the low coherence light source such as an LED, utilize in OCT because for the less path length. Okay, the smallest, as we discussed in So these three are not correct. Option C is correct. And why is it correct? Because the interference signal to be localized in a very specific depth. So the small alignment, misalignment, if you have, so that can also have it can also give the proper signal if you have small misalignment. Okay, so this is why, to allow the interference signal to be localized in a very specific depth, so we need to use the precise alignment actually, and that's why low coherence light is utilized for that, to get the interference signal. Okay, moving towards the next question. The Frenzel-Arago law states that the visibility of the interference fringes is zero when the two interfering light waves have A. orthogonal polarization states, B. the same linear polarization, C. low temporal coherence, D. identical frequencies but different phases. Let me know what is your answer for this. So in the previous question you said D, but it's not D, this is C, I think. Okay, what about this one then? Please tell your answer. Option A. Where it went? Orthogonal polarization states. We have discussed, I think, this one. Do we?
We have discussed this.
Yeah. Here. Yeah. So the visibility multiplier is cos theta. So here, yeah, you are correct actually. Orthogonal polarization states. Why? Because the vertical and horizontal polarization doesn't interfere with each other, and that's why we are getting the zero interference, and this is called a orthogonal polarization states. Like this is the answer for that, correct answer. The same linear polarization it won't be. low temporal coherence and identical frequency but different phases. It's not correct. So this is the orthogonal polarization states. Okay. What about the next one? How does a polarization maintaining PM fiber prevent random polarization evolution? Option A, by coating the cladding with a metal that reflects all polarized light. B, by breaking the degeneracy between the two orthogonal HE11 modes. And option C is mentioned by ensuring the light only propagates as a circular polarization. And option D, by using a perfect circular core to eliminate the bifringence, all bifringence. Let me know your answer. Option B. That's true. By breaking the degeneracy between the two orthogonal HE11 mode. And why is it so? Because it will introduce a stress element, and that stress element will generate the phase modulation. And in the fiber, what is that? Yeah. So to ensure the have different phase constraint, reducing coupling between them. Okay. So the PM fiber prevents random polarization evolution because of by breaking the degeneracy between the two orthogonal HE11 modes. Understood? If you have there is no degeneracy, there is no break in the degeneracy, then what will happen? It will behave like a SME fiber. What was that? SMF. Yeah, SMF fiber, like this. So here the beta odd and beta even is equal, but here it's having degeneracy, and that's why this phase sensing stabilizes, but here it's not reliable. Moving towards the next question, in the phase generated carrier PGC technique, what is the purpose of the differentiate and cross multiply scheme? Option A, to shift the acoustic signal to a lower frequency to avoid 1 by f noise. Option B, to increase the optical power of the signal before it reaches the detector. C, to extract the phase information phi t in a linear analog form. And option D, to compensate for the low gain of the semiconductor laser. Please let me know your answer. These are not correct. We have discussed about the PGC technique already. Option A, you are saying? Option A, what we have discussed about this? Somebody wants to join maybe. So here PGC is different from the 1 by F baseband burial. So you can correlate both each other. So here, to shift the acoustic signal to a lower frequency to avoid 1 by F noise, it's not the correct answer for this. So you are wrong for this answer, but previously you have done very, very good. Here the correct answer is option C. To extract the phase information phi t in a linear analog form. So what it happens is like it extracts the phase information, and using that extracted information it forms a linear bezel, and it also separate out the noise, or what you're saying, that cross multiplying in the signal, in the linear signal. Okay, so it is this is the correct answer for this. So in phase generated carrier technique, purpose of the differentiate and cross multiply is extract the phase information phi t in a linear and analog form. Option D, to compensate for a low gain of a semiconductor laser, it is not related to this. And also option B, to increase the optical power of the signal before it reaches to the detector, it is also not correct. Power it is not enhancing or increasing, amplifying. Okay, so the correct answer is option C. So it retrieves your linear analog signal. Okay. So the next question, according to the laser theory discussed in the material, what is the primary source of fundamental phase uncertainty in a single longitudinal mode laser? Option A, thermal fluctuation in a semiconductor substrate. B, the use of 50-50 couplers in the interferometer. C, the inevitable byproduct of spontaneous emission. And D, mechanical vibrations of the laser's internal housing. So what do you think about this? Please provide your answer. Are you giving any answer? We have few more questions and we'll wind up after that. Spontaneous emission, you are correct. Option C. Yeah, we have already discussed about this one, that according to the laser theory discussed in the material, what is the primary source of fundamental phase uncertainty in a single longitudinal layer. So we already discussed about this thing, that spontaneous emission, how to reduce spontaneous emission, everything. High Q laser also we discussed. So option.
Can you please tell me how to reduce the spontaneous emission? I have missed that
Yeah,
part.
yeah, we'll go there to the slide first. We can see here where it was, temporal skin. See here, the fundamental source noise. So in the fundamental source means, it means laser is having noises in terms of, there are so many things. lasers can also generate spontaneous emission, because it is the lasing happens because of the spontaneous emission. Then, like, the spontaneous emission source or something, then it is amplified as a stimulated emission. So photons are multiplying and multiplying, and after that you are getting the lasing. In epic cavity, what happens, that two mirrors are there. One is almost opaque, which is 100% reflectance mirror. Another is 99.9% reflectance mirror. So once it is uh, getting that much intensity, or you can say the threshold, if it is reaching, then it will start releasing the lasing coherent light outside. So along with that, sometimes spontaneous emission, like a normal LED light also, like not a LED actually, normal broad band also can come. So to avoid that, we need to use high Q cavities. High Q cavity means it can be achieved. You can see here that how the FP, total internal reflection, is happening inside, like this. Okay, whatever this is. So it is going till here. Maybe I'll like this, like this, like this, and again coming back. So because of this back and forth propagation of light between two mirrors, highly reflective mirrors, it will amplify the signal, and that's why we are getting the spontaneous stimulated emission. And stimulated emission, you know already that if it is a coherent light, it will be having the particular phase. But in spontaneous emission, what will happen, the photon doesn't have the particular phase which is coming out. So that's why we need the very high Q cavities. If you have the high quality cavity which is having the high finish, so after keeping the um, um, optics, different optics, we can reduce it. The spontaneous emission we can reduce also by locking the phase output into a pristine narrowband state. Okay, so did you understood what I am saying?
Yeah, we got it.
Yeah, so the spontaneous emission you can reduce by either locking the phase, but you need the very high Q cavity. And high Q cavity doesn't mean that it will be like very cheap, or it's a normal price you will get. Very high prices will be quite high, because the crystals or the reflective mirrors will be costly for that, for the laser. And there will be optics. There are so many optics involved in that, notch filter, edge filter. So those things also, it will reduce some kind of spontaneous emission in that. Okay, so this spontaneous emission is the problem for this particular what we discuss about this fundamental phase uncertainty. So it will come as a random phase, with a random phase, and it will destroy our signal, which is generated by the stimulated light, stimulated radiation. So that's why we need to avoid this inevitable byproduct of spontaneous emission. We should avoid its spontaneous emission itself. Okay, so this is not correct. 50-50 coupler for interferometer. Thermal fluctuation in a semiconductor substrate, this is not correct. Mechanical vibrations of the laser's external housing, this is also not correct. Moving towards the second last question, I think this is, which question is, yeah, second last question. When optimizing a PGC system, y is crossover point of Bessel functions J1 and J2 chosen as a bias point for the phase carrier amplitude phi c. A. To ensure that the interference is always destructive at the carrier frequency. B. To ensure the product J1 phi c, J2 phi c remains stable despite small fluctuations in phi c. C. To eliminate the need for a low pass filter in a receiver. And D. To minimize the total power consumption of the piezoelectric transducer. So what's your answer for this? Is it B? D? Remains stable despite small fluctuation. Yeah, it's correct. So what is happening in this? The ensures the product of J1 phi-C and J2 phi-C remains stable despite small fluctuation. So what is happening? The J1, if it is increasing little bit, so J2 maintains such a way that it will decrease little bit. So the product of both, instead of the small fluctuations, the phi-C will be constant. Okay. So the basal function J1 and J2 chosen as a bias point for the phase carrier where the for phi-C. So the crossover point where if the product one is increasing, another will decrease automatically and it will stabilize the phi-C. Okay, so it's called a crossover point. Okay, this is good, you are doing good. This is not correct, this is also not correct, this is also not correct, this is correct. Moving towards the last question. A high Q laser cavity with highly reflective mirrors leads to a longer photon lifetime tau ph. How does this affect the phase uncertainty del phi del theta of the laser? Option A, it decreases the phase uncertainty. B, it has no effect on phase, only on the output intensity. C, it forces the laser into a multi-mode operation mode. Then D, it increases the phase uncertainty due to more spontaneous build-up. So what's your answer for this? Actually, you are doing very good. Almost 1, 2, 3 questions answer you have given wrong, but out of 12, out of 11 you have given 3 out of 11. You have almost 8 questions answer you have given correct. Please give your answer for this question. Is it A? The phase uncertainty. We have discussed about this problem that del theta is equal to under root 1 by tau photon ph. Now you can tell it decreases the phase uncertainty. This is the phase uncertainty. So a high Q cavity laser with a highly reflective mirror leads to a longer photon lifetime. How does it affect this? Okay, so if it is longer, then it will decrease the phase uncertainty. It's correct. This is the correct answer for this. It has no effect on the phase, only on the output intensity. It's not correct. It forces the laser into multi-mode operational mode. No. It increases the phase uncertainty due to the more spontaneous build-up. This is also not correct. So you are correct again. So option A is correct here, and you have given 9 correct answers. So you should get something benefit from some chocolate or something, toffee. We are doing good. You can join all the classes, upcoming classes. Okay. Are you hearing me?
Yeah. Thank you so much
Yeah.
for the class.
Yeah.
We'll try by 11 to start in the next
Yeah. Yes.
sections.
Next week, tomorrow also is there one class.
Yeah, sure.
Tomorrow afternoon you can join.
Yeah,
I'll give another the various questions again. Interesting
Okay.
questions. So yeah, for today I think this much is enough. Already we finished. If you have doubts, you can ask me. We have so much time now. Almost 40 minutes we have.
Maybe tomorrow I will ask. Let me go through this one more time. So that I will
One by
make
one
it
I should go.
more
Okay.
to this.
Okay,
Yeah.
I'll take you from one by one. This is the fundamental direction dilemma, where I discuss with you the phase propagation. Photodiode are not useful for the phase detection. Then we need optical demodulator, where it will change the phase to intensity, and after that detector works. Then we have discussed about the two interferometers. One is free space and another is all fiber. Free space we need very precise alignment, otherwise it will not be it will not give the proper phase. It will have the phase mismatching. So some micron mechanical drift also it will make the ruin the setup, and that's why it is useful for the highly controlled laboratory environment. But where the another one is all fiber is for perfectly, like it can be used in perfectly in any environment, but it's because we are using the fiber, it will be having the thermal sensitivity and the fiber birefringence issue also, with the birefringence issue. So but it can be used for the pipeline monitoring and deep sea hydrophones. Also we discuss about the uh, challenges associated with the phase sensing, temporal coherence, polarization drift, environmental noise, fundamental source noise. So temporal coherence we discuss about the source line with matching. If we just tune it source line with matching, then temporal coherence will go away. Then polarization drift, where the polarization maintaining fiber we need to use. Then environmental noise, if you have something which is giving the noise and changing your mm, signal, so it can be avoided by using phase generated carrier PGC. Then we discuss about the fundamental source noise, where high Q cavity lasers can be used to reduce the spontaneous emission, and which is ruining the detection system because of the uncertainty of the phase of spontaneous emission. So high Q cavity lasers can be used to avoid such kind of effect. Then we discuss about the temporal coherence, whatever we discuss here in detail, where terahertz, gigahertz, and kilohertz signals we discussed, how the broadband LED, Fabry-Perot laser, just a second, Fabry-Perot laser, and DFB, very um, narrowband laser, how it can be utilized for the different application. Then what are the uses application of this particular types? So OCT, then short range laboratory sensors, then OTDR and LIGO remote hydrophone, there we can use. Then fringe visibility envelope. So this is like a packet we discussed already, where the path length difference and the intensity is mapped, spectra is mapped like this, plotted like this. Then degree of coherence G12 we have discussed. Okay. Then coherence length also, with between this coherence length is quite high compared to this 2LC. Then the low coherence optical coherence tomography we discussed, where the scan depth probe can also penetrate through the tissue. Okay, tiny 20 micron interference window through the tissue depth. So through the tissue depth actually, not tissue. Yeah, so the path length must match precisely with the fringes of to appear isolated in depth. Then we discuss about the fringal Arago limit, where the visibility multiplier is cos theta is equal to cos theta. Okay, then orthogonal polarization, theta if it is 90 degree, then it is dot product is 0. Okay, then we discuss about the PM fiber architecture, why it is important, because we need the break to break the degeneracy. If we are breaking the degeneracy, then we are getting the phase sensing stable, like phase sensing can be utilized, can be used as a PM fiber is basically useful for the phase sensing stabilization, where the SMF lacks its capability, because this HE11 mode is almost equal, the beta of E1 and odd is almost equal, both modes are equal, so it can't be used. Then we discuss about the 1 by F baseband burial, where we saw, you can see here that before how it is looking, your intensity and frequency spectra. Then after using the PGC, how it is enhanced. The 100 Hz signal sideband can be seen here, that how FC, 2FC, 3FC is enhanced using the phase generated carriers. Okay, moving towards the next thing, the differentiate and cross multiply array. We already discussed about this schematic. Then also we have discussed about the source phase noise, because of the spontaneous emission, again that it's random phase angle, it has it ruin our signal, so we need to avoid this. So using the high Q cavity, where the phase variance is inversely proportional to tau A. Then this is the master phase architecture, where the laser, coupler, and then reference and sensing fiber will be there. Then again PM coupler is there, photodiode, then PGC, and all these things are after detection, photodiode. Yeah, so we have finished now. Still, if you have doubts, you can ask me.
Is this spatial coherence has in the role of this phase modulated sensor?
Here?
Yeah, spatial coherence. When I'm talking about entirely about the phase modulated sensors, we discussed about temporal coherence.
Yeah.
I want to know whether this spatial coherence plays a role in this phase modulated sensors.
Usually we need to discuss about the temporal coherence, because everything is happening with respect to time, and spatial coherence already we discussed. Using this lasing itself, you'll get the spatial coherence. You're talking about the phase coherence or what?
Spatial coherence.
Which slide you are talking about? Just let me.
I think the temporal coherence one slide is there. Challenges of. I think you should go to the first or second slide.
This one you are talking about?
No. Yeah. This one.
So what's your answer? What's your question actually?
Like, what's the role of temporal coherence? We have discussed.
Temporal
But
coherence, because everything, the sensing application is based on the temporal sensing. Each and every moment we need to sense. So that's why we need to use such a particular source which is having the application based on the source. The application can be used based on the source. So source we need to define it. So the temporal coherence is means like the broadband LED if you are using. So it will be having, obviously it will be having the like a broadband. Here it is mentioned, you can see here, and the coherency will also not that much good. The LED, it doesn't have that much coherency. Where it can be used, optical coherence tomography, and the length you can see 20 micron. It's a very near field you need to go, and after that you need to sense it. So this is the disadvantages. And after that we are seeing about the very spatial like temporal coherence in terms of very what you can say, narrowband laser or high Q laser, high finish laser, so where you can use up to 10 kilometers also sensing. So there it comes as a temporal coherence into a picture. Did you understood what I'm saying?
yeah, I got it.
So if you are using the broadband, you need to go very nearby and the application will be limited. While
Okay.
if you are using the DFB laser, it will be having the coherency very high, very high, so it can be used for the kilometers of sensing. And because sensing is happening temporarily, everything, you need to, each and every moment we are sensing something, so we need to have such uh, light source which can tackle it. So the best example, if you want very fast and nearby, then LED is best example. Then if you want to go for the few coherence length and a few the full width half maximum is up few nanometer, then Fabry Parrot cavity is best. Short range laboratory sensors. And if you want to go for kilometers, meters, then you need to go for the temporal coherence, which the laser which is having the high temporal coherence, which is narrowband laser, DFB, distributed feedback lasers. Okay, that's what I was discussing here. So the lasing, it's like it's looking like a epic cavity, Fabry Parrot. But if you want high Q cavity, then you need to go for the distributed, the layer by layer cavity, like this it will be. So refractive index will be different for each slab of the material. So suppose here it is high, then here it will be little bit low, then here it will be little bit high. So what will happen, once the light source is generated and cavity, the cavity, what it does is, it will capture the light and trap it inside. Suppose this is high, so it will trap it inside this, then slowly it will send to another one, then it will be like this. So the Fabry Parrot itself is the best lasing cavity, but it's very costly and making it is very difficult. So that's why usually people use the cavity which is Fabry Parrot. Understood?
Yeah. Okay.
Okay, then next class we'll again refine it. I just took it a broad way. I need to go into deep for the next session. So we'll discuss more about the problems associated with the phase sensing phase modulation sensing and application also. We need to go through the proper applications, how it is where it is useful, and how we are extracting the data, proper data. Okay, so for a while I am just stopping here this session. We'll meet tomorrow afternoon. Please join again.
Okay, thank you so much.
Yeah, you too. Thank you.